Today's talk will be given by Michael Polese. Michael is an associate research scientist and a part-time instructor at Northeastern University in Boston, Massachusetts. He received his PhD at the Department of Information Engineering of the University of Padova in Italy. He was also an adjunct professor and postdoctoral researcher at the University of Padova. During his PhD, he visited New York University, AT&T Labs, and Northeastern University in Boston, Massachusetts. He has collaborated with several academic and industrial research partners, including Intel, Interdigital, New York University, AT&T Labs, University of Abo, King's College, as well as NIST. He was awarded the Best Journal Paper Award of the IEEE ComSoc, Outstanding Young Researcher Award from IEEE ComSoc, and several Best Paper Awards. His research interests are in the analysis and development of protocols and architectures for future generations of cellular networks, 5G and beyond, in particular for millimeter wave communications and in the performance evaluation of complex networks. In this talk, Michael will focus on softwareization, virtualization, and disaggregation of wireless network functionalities, which has been identified as key enablers for flexible data-driven 5G and beyond networks. Particularly, software-defined cellular networks can satisfy the new application-driven traffic requirements, and as well as support highly time-varying topologies and interference dynamics. Because of their openness through well-defined interface and programmability for swift response and network optimization. So I would like to welcome Michael. Good morning, and welcome to our AI and Machine Learning 5G Challenge webinar series. Thank you so much for joining very early.
Thank you for the kind introduction, and good morning, good afternoon, or good evening, everyone. So I'm going to share my screen with the presentation. As Thomas was mentioning, today I will give a brief talk on how next generation networks, mainly 5G, but people are also starting to think about 6G, are transitioning toward an open, programmable, and virtualized architecture. This talk is based on a few contributions, mostly from the Institute for the Wireless Internet of Things at Northeastern University, which is the place where I work now, and especially with colleagues Leonardo Bonatti, Salvatore Doro, and Professor Basagna Melodia, and a contribution a paper that I wrote when I was at the University of Padova in collaboration with AT&T. And you can find all of these papers online if you are interested for a deep dive on these topics. So the outline for today is this. I will start by discussing how why and how networks are transitioning to openness and programmability. And then I'll describe what we mean with 5G open, programmable, and virtualized architectures. And this will be the first half probably of the talk. Then in the second part, I will discuss how we can embed into these networks intelligent control using ORAN, the recent initiative launched to open 5G networks. And I'll discuss two use cases, one related to load prediction and the other related to scheduler selection. So I think it's always good to start by asking, why are we doing this? So why do we need a new architecture, and why isn't what we have in 3G, 4G, or early 5G deployment good enough? And you can answer this by assuming two different perspectives. If you think about the key performance indicators that you want to satisfy on your network, then you have that 5G has been introduced to support a very diverse and heterogeneous set of use cases. So 5G supports enhanced mobile broadband, so very high throughput, ultra low latency communications with high reliability, and supports communications for a massive amount of sensors, or for example, for cyber physical systems and the IoT. So from a performance perspective, you need a flexible and programmable network architecture to be able to address the needs of these different kind of use cases. From the operator perspective, you need a new architecture, an open architecture, because the complexity of the networks is increasing. So when going from 4G to 5G and then 6G, we're going to have more devices, so more, and also more heterogeneous devices with different capabilities, with different requirements that can be static, can move, as for example UAVs, and so on. We are going to use more spectrum. So for 5G networks have already transitioned toward the support of the millimeter wave spectrum, as you may know. And as you can see here, there are a number of challenges related to supporting millimeter wave or different portions of the spectrum. And these need to be implemented, and solutions to these challenges need to be implemented and factored in the network. And finally, you have more complex protocol stacks with different portions of the network interacting together and cross-layer effects arising from resulting from these kind of interactions. So managing these networks is a really complicated proposition for network operators. So this is why we need an automated and intelligent network architecture, so that the operations of network operators can be automated and operated through some intelligent algorithms. So these are the main motivations that are driving this kind of revolution toward more open and flexible network architectures. And the reason why we are talking about this now is that the approaches that were adopted for previous generations of cellular networks are not do not fit this kind of requirements. So the approach that you had in previous cellular networks was that of a black box architecture. The telecom operator used to buy equipment from a vendor, and without actually getting access to the equipment or getting the possibility of programming, optimizing, or configuring in a very flexible way the equipment bought by a certain vendor. So what the operator sees is that packets get in and packets get out from a certain network, but the operators do not have control of the equipment they buy. So there is limited reconfigurability and adaptability. And you may already see that this makes it harder to match the requirements, the flexible requirements of a 5G network. You also have limited coordination and vendor locking, in the sense that it's difficult to merge together equipment from different vendors. So the telecom community, and especially operators, have been pushed toward a new kind of architecture, which is more open and is based on three key principles that I'm going to discuss in the next slide. So virtualization, disaggregation of network function, and open interfaces among the different network functions, and the possibility of programming this network function. So to not have anymore a closed solution in which you cannot do anything or that you cannot modify, but the possibility of having programmable network nodes and having closed control loops in which you can run some kind of intelligence. And the behavior of the network really transforms because you have much more control and granularity in defining what a packet sees when it traverses the network. So in a certain sense, this is the adoption, this step represents the adoption of some paradigms that are now common in wired networks, like software-defined networks and virtualization. And bringing these to cellular networks is requiring a larger effort, but is something that is happening right now. So let's discuss these three building blocks of future open networks. So with virtualization, the functionalities of a certain piece of equipment are implemented through software rather than being implemented through hardware with a specific firmware, and run on white box hardware. So they can run on a generic piece of hardware. And these functionalities are represented by so-called virtual network function. So a network function is something that provides a service, virtual in the sense that it is virtualized. And to make this work, we need three pieces. So the virtual network functions, which are the services that we need. We need the network function virtualization infrastructure, which provides basically an abstraction layer over a generic white box physical hardware with a virtualization layer and different technologies to concretely implement these virtual network functions. That can be virtual machines or containers and so on. And in addition, on top of this, you also need a network orchestrator. So something that manages the life cycle of each network function. So for example, instantiation of a virtual machine, orchestration of the resources so that you know that you have resources available to run your virtual machines or containers and so on. The second building block is disaggregation and open interfaces. So rather than having a single piece of equipment or a single network function that does everything that, for example, your base station requires to do, with this kind of architecture, you have multiple pieces of equipment or network functions that do, for example, in this case, what a base station used to do. So in a 4G network or previous generators network, these layers are all in the same piece of equipment. Instead, with 5G and with proposals from 3GPP, the base stations are now split into three different units: the centralized unit, which contains the higher layers of the protocol stack; the distributed unit, which contains the RLC, MAC, and the higher part of the physical layer. So these three layers are layers that need to be run on the same piece of equipment as they require a very tight synchronization. And then we have the RU, so the radio unit, in which you run the RF part and the lower part of the physical layer. So you have different pieces of different functionalities that are split into different pieces of equipment or network functions. But the main novelty is that the telecom industry is requiring that these different network functions are connected through open interfaces. So through interfaces that are standardized, that provide a specific set of functionalities so that you can, for example, connect the CU of a certain vendor to the DU of another vendor, or you can connect both of them to a control plane provided by an additional party. And this really opens the possibility of doing several things in your networks, goes beyond vendor lock-in, allows you to tap into these devices and control these devices from using these open interfaces. The third key element is the availability of programmable network nodes and control loops. So given that now everything is virtualized, so everything runs on software, it's easier to implement programmable logics. But besides this, the availability of open interfaces allows you to add interfaces that gets data, analytics, and telemetry from the RAN. And you know that this is key to implementing machine learning and artificial intelligence solutions. So you need data to train your networks. But besides this, the fundamental innovation is that the controllers can use this intelligence to make some policy decision or to decide some commands and send them back to the run functions. So what you have is a closed loop control in which some intelligence is added in the loop without the need for some manual optimization or for some human intervention, because everything happens in this closed loop. So these three building blocks, the virtualization, the disaggregation and open interfaces, and the programmability of network nodes, are at the basis of a new network architecture for 5G and beyond. So let's take a look at this figure, which is quite complex because it gives you the idea of the complexity of these kind of networks and of the different functionalities that are implemented in the different portions of the networks. And these three building blocks now allow you to run this network using software-based solutions rather than hardware-based solutions and specific pieces of specific components and costly pieces of hardware. And so we have different projects that have embraced this software-based networking approach for cellular networks, and that are providing protocol stacks for the different components of these networks. Starting, for example, from the RAN, where you have a couple of software projects like OpenR interface and SRS-LTE that provide you LTE protocol stack that are currently implementing NR. So NR is the representative specs for the 5th generation of cellular networks in 3GPP, and as the implementation of software-based protocol stacks for NR is currently ongoing. And they also provide software implementation for mobile terminals, so user equipment. In addition, we have a couple of projects like the software community in the ORAN Alliance and the SD-RAN project from ONF that are targeting implementations, open source implementation of some parts of the 5G base stations. So as I was mentioning, the central unit and the distributed unit. And we have software project also. These are from ONF to enable edge cloud solutions. So to place caching or controllers at the edge. We have open source software projects that are involved with the 5G core or the legacy 4G core. And we have other projects that provide orchestrators and network automation platform like ONAP or OSM. So there is a very rich and complex ecosystem of software-based solutions, open source. This is really key. These are open source software-based solutions that you can download, use, extend to run a software-defined 5G network. So if you want to know more about this kind of open source software, these are a couple of useful resources. And in particular, we recently launched a website called open5g.info, which contains a list of software projects that you can use to either instantiate a programmable 5G network or to basically tools that you can use for your research on 5G networks. And the website itself is open source in the sense that it is hosted on GitHub. And if you think you have a project that is worth adding to this list, or you want to update some information, you can open, for example, pull requests and contribute to the development of this website. So we are trying to make it as a resource that can be used by the community in general. All right, so this closes the first part, which is what are the building blocks of open and programmable 5G networks, and leads us to the second part. So what can you do with these kind of building blocks? And specifically in this second part, I'm going to talk about ORAN and what are the capabilities that ORAN implements in these open and programmable networks. So ORAN the ORAN Alliance is proposing a reference architecture to implement programmable approaches in 5G networks. So this is in general the kind of architecture that they introduce. It is based on open and standardized interface. So like this E2 interface, the O1 interface. It is based on the principle of a disaggregated run. So the different components run different network functions. And as a charter that is specifically focused on open source contributions. But the main innovation that ORAN introduces is are the RAN intelligent controllers, which are two network functions that can be plugged through these open interfaces to the radio access network and can perform some control and optimization of the radio access network. And in particular, they can allow you to embed in the network intelligent control loops. So control loops in which you have some, for example, machine learning or some optimization running in the RIC and executing in the running in the RIC and performing decisions related to the run. So these control loops closed control loops are really something new in cellular networks because they basically short circuit the need for manual optimization of these networks. And ORAN is currently considering the first three control loops, the first three use cases from this slide. And they are basically operating on a time scale that is above 10 milliseconds. So the first loop is this one between the two RICs and runs on the A1 interface, and for example, can be used by the no real-time RIC to perform policy decisions or slicing decisions on the near real-time RIC. The second loop runs on the E2 interface at near real time, so between 10 and 1000 milliseconds, and can control user session, like perform load balancing, handover, and so on. The third loop runs between the near real-time RIC and the DU and can control medium access parameters like the scheduling policy, how you do run slicing, and so on. But besides these three loops, we think it's worth adding more intelligence to the network with something that ORAN is considering for further studies. So loops that run between the DU and the RU. So for example, for radio management, or loops that run in the device itself. So for example, to do learning at the physical layer. So these two loops are currently not supported by ORAN, but so the purple loop is currently for further studies, so it may be supported by ORAN in the future. While the bottom loop, the pink loop, is not currently supported by ORAN. But we think it's something worth investigating, as it could add some really interesting capabilities to this kind of networks. So in this final part, I'm going to talk about two use cases that you can have when using these intelligent control loops to implement some intelligent behavior in 5G networks. And the first one is data-driven clustering and load prediction. And the second one is a scheduling selection based on deep reinforcement learning. So the data-driven clustering and prediction use case is something based on the study that I did with AT&T, and is based on a very rich data set from AT&T with more than 400 base stations in San Francisco and almost 200 base stations in Palo Alto. It's a 4G deployment, and the data that was available was related to the PRB utilization, the number of users in the networks, and the number of handovers. So we used this dataset to do a couple of studies and to study how data-driven operations can that are run in the RAN controllers can improve the performance of the network. So the first item that we studied is how the network can automatically match the RIC, the controllers, and the CUs with the goal of minimizing the interaction among different controllers, because when different controllers need to interact, they need to sync up and need to exchange some context information. So for example, when the user transitions from one CU controlled by the RAN controller on the left to the CU controlled by the RAN controller on the right, the information about the user needs to be synchronized among different elements of the network. And this increases your control plane latency. So our design choice was to use data-driven clustering by trying to minimize the inter-controller interactions because they have an impact on the control plane latency. So what we did was a data-driven clustering based on the handover transition. So base stations which have a higher probability of seeing a handover between a certain users are clustered together. And you can see a comparison between a static approach on the left. So this is what you can do when you don't have RAN data and you go for a fixed non-programmable approach. So a configuration that you run once and you keep at least for some days while you run your network. And on the right, we have a data-driven approach in which the association between base station and controllers is based on network data and is dynamic. And you can see, for example, a very interesting behavior. So this is the area of Palo Alto, and you have a railway that is running basically from the top left to the bottom right corner of this figure. And you can, so a line represents the probability of handover, and the thicker the line is, the higher is the probability of having an handover. So you see that you have a lot of handovers going on along this railway, so along base stations of this railway. But a static approach that is not based on network data does not allow you to capture this behavior. So this clustering, for example, is based on the positions of the base station. But instead, if you can capture this network behavior, you can see that you have a lot of handovers from this base station, and you can cluster them together. So you can see that so colored lines are for handovers between base stations in the same cluster, while black lines are for handovers between base stations in different clusters. And you can see that we have many more colored lines here on the right than on the left. So this data-driven solution allows us to decrease the number of inter-cluster handovers. So you can see here, this is an example from running the algorithm on a certain day. You can see that the position-based clustering increases the number of interclustering handovers, which impact your control plane latency, while the data-driven clustering keeps this number low. And to further elaborate on this, on the bottom, you see the ratio between intra-cluster, so handovers which have a very limited latency, and inter-cluster handovers. And you can see that the ratio is higher when we consider data-driven clustering rather than position-based clustering on the bottom. And here we were considering 15 minutes updates or daily updates. And you can see that during the day, the performance is rather similar, while at night, when the network is less stable because you have fewer users, it's probably better to go with a daily update rather than a 15 minutes update. And this is robust also to the number of clusters that you consider. So you see we have an almost constant gain for this ratio between data-driven clustering and position-based clustering, even by increasing the number of clusters. So the second use case that we studied with this dataset is how can controllers improve the predictions of the number of active users in your network. So to do this, we compared a local-based method, so a method in which each base station predicts the number of users for that base station. And this is what is possible with, for example, 4G networks and with the black box approach that I was mentioning at the beginning of this presentation. So you have a closed piece of hardware in which a vendor has implemented this functionality, but you cannot have it synchronized and coordinated among different base stations. Instead, with the ORAN controllers and with the open interfaces, you can have a cluster-based prediction method in which you train a model for a cluster of base stations. You train a model on the controller, on the RIC, and predict a vector with the number of users for all the base stations belonging to the RIC. And this basically allows you to exploit some spatial correlation to improve the prediction. So let's, I'm not, for the sake of time, I'm not going into detail on all the algorithms that we tested and the details on data processing, training, and testing. But if you are interested, you can take a look at this paper on the bottom where we provide all the details related to this. Okay, on the top, we have some results for a sample cluster which has these base stations in the San Francisco area. So we tried a Gaussian process regressor based on with the cluster approach, a random forest with a cluster approach, and some local solution. So a local-based random forest, a local-based Bayesian regressor, and a local-based Gaussian process and ARMA. And we are predicting the number of users at different, at the medium time scale, so for lags of 5 minutes. So at most 45 minutes in the future here. And you can see and on, that the no cluster-based approaches, even though may perform well for short-term prediction, their prediction error really increases when going toward the right. So when going toward higher lag predictions. Instead, the cluster-based approach, which is the best for the even for the short-term prediction, the RMSE of this approach does not increase as much. So cluster-based approach exploit this spatial correlation between the base stations and can automatically infer and improve the prediction performance. And if we take a look at the average results on all the clusters, you can see that the performance still remains the best with the clustering approach. Okay, so let's transition now to the second use case, which is related to scheduling selection with deep reinforcement learning. And for this, we consider a slicing environment where you have your base stations that needs to support user with the different traffic types that I was mentioning at the beginning of the presentation. And this represents a challenging environment. So you have a dynamic channel and you have a dynamic resource allocation for each slice. So the slices may be given different amount of spectrum in time. So to manage this complex and challenging environment, we propose to exploit some data-driven closed control loop with the near real-time rig to automatically tune some RAM parameters for each slice. And in particular, in this study that you can find on arXiv at this moment, we focused on how we can select the optimal scheduler for each different slice through deep reinforcement learning. And the nice thing, I would say the really interesting thing about this study is that we implemented everything using the real ORAN software on a one of the world's largest network emulator. So Colosseum is an hardware-in-the-loop network emulator, which has more than 200 software-defined radios, tens of gigahertz of emulated bandwidth. It's a really massive data center with more than 20 racks of radios, 170 high-performance servers with CPU, GPU, and FPGAs, and has massive computing capabilities. So it has more than 900 terabytes of storage, 320 FPGAs, and so on. So it's a really interesting tool to study these kind of problems where you have to combine a white box run with some intelligence that can run at the edge. So we use Colosseum to create and test complex 5G scenarios. And in particular, we implemented a fully virtualized run based on some open source software, which in this case is a combination of SRS-LTE and the ORAN contribution for the interface on a complex scenario. So we basically emulate the channel scenario for a scenario in Rome with 4 base stations and 40 users. So each base station has 10 users, and we have 3 slices per base station to support the different types of traffics. But and this is the infrastructure that Colosseum already provides. What we did is we added the ORAN infrastructure on top of this. So we integrated the the open source software components provided by the ORAN Alliance in Colosseum to control the base stations running in real time. And for example, we implemented a few XHubs. So what you can run on the near real-time rig is called XHub, in which we have DRL agents controlling in real time the base stations running in Colosseum. And I think this is a very interesting approach. And so to elaborate further on the ORAN and infrastructure, we have 12 agents running in parallel to control the slicing for each base station. And each of them has a fully connected neural network with 5 layers and 30 neurons each. And we have an autoencoder to basically feed the base station data to these XHubs. We do offline training with 6 GB of data and 63 hours of experiments run in Colosseum, so in this dense scenario. But the inference is performed online. So we get real RAN data through the E2 interface that is then fed to the DRL agents, which perform some inference in real time. And the inference that it performs is actually a decision on the scheduling policies that can be run on each base station slice. So round robin, water filling, or proportional fair. So we have these 3 schedulers, and we need to decide which should be used for a certain configuration in a certain slice. And to show you a couple of experimental results before finishing the talk. So you can see that the DRL-based approach in the purple dotted line improves both the spectral efficiency of the MBB slice and the resource allocation in the URLLC slice. And besides this, it can reduce the buffer occupancy at the base station by 20%. So it really gives you a performance improvement. And the reason, so to motivate why we need a dynamic approach, we plot here the probability that the DRL agent selects a certain policy. So the proportional fair, the water filling, or the round robin, according to the number of PRBs, so the size of the slice. And remember, this number of PRBs changes dynamically during the experiment. And you can see that each slice, so each color, has a different behavior according to the size of a slice that you select. So the larger the circle, the higher the probability of selecting that configuration. And for example, the URLC slice, when it has a limited number of PRBs, selects almost equally the PF or the WF scheduler, while the EMBB slice selects either the WF or the round robin scheduler. So you have different behavior for different slices and different behaviors for different slice sizes. So this is why we need a data-driven adaptable approach. So this is another motivation behind why we think it's really interesting to go toward this kind of paradigm. So to conclude, I hope that what the take-up message that I would like you to remember from this talk is that future cellular networks will be open, will be programmable, and will be virtualized. And these 3 building blocks truly enable the vision of data and AI-driven networks. So these building blocks allow you to embed intelligence in your network. And there are a few steps to take in the road ahead. So we need testbeds and platforms for deploy this run and test these intelligent runs. We need datasets, and we need more involvement toward the development of these open source protocol stacks, because the more people contribute toward this, the better these products in the end will result. So a couple of resources. This is the website that I already mentioned earlier, with information on the open source 5G stacks that you can find online. This is the Colosseum website. So Colosseum is open to the community, to the research community, and you can use this website to investigate more. And this is the website of other testbeds available here in the United States, running under the Power platform, which you can use, for example, as dataset factories. And finally, this is the website of the Institute for the Wireless Internet of Things, which is the research institute where I work. So I thank you for your attention, and I'm open for any questions that you may have. Thank you very much.
Thank you very much, Mikhail, for the nice presentation. I think it's quite interesting to see how the open interfaces and other open SDOs are coming up to just add on in the 5G space. I have like some questions, as well as we have also some questions that we can see in the Q&A, as well as the chat window. Of course, if other participants or other people on the call have questions, they can write them on the Q&A window so that we can take them during this session. We still have some time. Now, as you are talking about, for example, the ORAN Alliance, it has been in existence, I think, for the last 2 years. There are some standard developing organizations, but if we can talk about the 5G use cases, they've been there for some time. These use cases and 5G pillars have been known like in the beginning, but in the past few years, the standard developing organizations, or what we call SDOs, could not predict the level of open approaches that are needed to achieve these functionalities or these use cases or these 5G pillars. Why was it the case that the SDOs could not predict these kind of open approaches that we can see now is an opportunity that, for example, ORAN is working on? And we also have, like in Linux Foundation, there are several projects that are working on also.
So your question is basically, why hasn't these open approaches been integrated in the standards from the start?
Yeah, why it was not integrated from the start?
Yeah, I think that you have two different standardization lines here. One is the technology. So basically the protocol stack that runs on the base stations, the core, and the user equipment. And that is what the 3GPP strives to do. And to be fair, the disaggregation is part of the 3GPP standardization. The core in the 5G network is completely virtualized and based on network functions. So the 3GPP has recognized the need for more openness and flexibility. What ORAN has added on top of this is the possibility of controlling what the 3GPP has standardized through these open interfaces. So I think there are two approaches that go side by side and emerge from two different needs. To recap, the 3GPP has actually considered some open approaches, but ORAN has developed on top of the openness that the 3GPP has already introduced. But I'm not involved in the standardization part, so this is something, this is my opinion, and I'm not part of any of these standardization organizations.
Of course, just talking on the ORAN topic, there's one question that popped up in the Q&A. It's more or less like asking, like, how can the ORAN, maybe ORAN specifications, be used in the file layer by file layer or researchers to test on signal processing algorithms? I'm not sure if we can quantify, or we can say that the ORAN specification can be used in the signal processing regime, but can you maybe comment on this?
Okay, so as I was mentioning earlier, the ORAN at the moment is not concerned with opening up and having an open programmable control loop at the physical layer. So channel estimation, data detection are are loops, control loops that run below the millisecond. So those are not part of what ORAN is addressing at the moment. And they probably need to be run in the DU or in the RU itself. So it does not make sense to have this kind of intelligence go through the run intelligence controller, the RICs, because it will take too long. So you really, when you think of how you can embed this intelligent control loop in your network, you really need to think about where you have the data, how can you move the data, what's the cost of moving this data, what is the latency related to moving this kind of data, and eventually what is the best point in which you can do this kind of inference. And if you take a look at the paper that I shared before on the intelligence control for next-G cellular networks, we discussed all of this. So where you want to, basically according to the kind of control decisions that you want to take and its time scale, we provide suggestions on where it should be placed and on how much ORAN supports that kind of solution.
And also, just digressing on the same topic, we were talking before about the openness. And of course, in the presentation, you have discussed about programmability.
Mm-hmm.
And if we are maybe we'd say forward thinking, looking into the future, can we say that the next step after programmability, is it autonomicity, like maybe to have autonomous networks, or can we say that the one leads to another thing, or are we going to a different direction?
Yeah. This is a very good question. So I think that programmability is a building block to have the autonomous network. So programmability and open interfaces allow third parties controllers to run and automate operations on top of, for example, protocol stacks and so on. So programmability is definitely an enabler for this.
Thank you so much. I was also so interested in the project. I'm not sure if I'm going to pronounce this correct. Colosseum.
Yeah, that's right.
This is quite a very interesting project, and you already indicated that it's an open project where anyone can benefit from. And I would see from your presentation there is quite a lot of work going on. Can you just clarify how, for example, our community here, the challenge, the participants, most people will be looking at the data set, how we can play around with the data for research, for the competition, the test beds, how can we use our solutions to maybe just benefit the community?
So Colosseum is a network emulator that has been developed by DARPA for the Spectrum Challenge competition and is now run by the Institute at Northeastern, and is open and accessible to research groups that are for free, for research groups that are funded by the NSF. For PIs and research groups that are not funded by the NSF, you can always reach out. You can use the website on top here and contact us to discuss how basically how you can access the testbed. So the best I can tell you is go to that website and look at the information that is available there. To give you some context on what you can do in Colosseum, so in Colosseum, the basic unit is this standard radio node, which is a server coupled with a software-defined radio, which is a USRP X310. So what you can run on USRP X310 is up to you. you can run GNU Radio, you can run, for example, we run SRS IDE, you can run the protocol stack that you want on these software-defined radios, as long as it matches the capabilities of the SDR. And yeah, as I was mentioning, it also has a data center connected to it, so you can use it to, for example, store data and so on. And in terms of data availability, we plan to make the data that we collected to do the experiments that I was showing you earlier publicly available. So the paper is currently under review. If it will be accepted, we plan to make the data that we used for the performance evaluation and the training of the algorithm publicly available.
Thank you so much. Maybe we can take one last question, and if we have more questions, maybe we can follow up offline. There is one question which popped up in the chat that can you elaborate on the Open Fronthaul 7.2 interface? What is the split, for example, in more details, and in the case of massive MIMO use case? So maybe just a quick overview of the Open Fronthaul.
The Open Fronthaul interface is compliant with a split that has been defined in the FreeGPP. So the FreeGPP has defined different splits of the protocol stack, and the industry has converged toward this 7.2 split, which is a split between the higher part of the physical layer and the lower part of the physical layer. So the DU, the physical layer in the DU, runs everything up to the generation of modulated IQs. These IQs are then moved through this open interface to the RU, which only does digital precoding if needed, and the FFT transformation. I'm talking about the downlink. The reverse happens in the uplink. So the RU does very simple processing, and most of the processing is actually done in the DU. And the Open Fronthaul interface, to answer more specifically to all more questions, is based on eCPRI. And on top of that, adds some control interfaces so that the DU can control what happens in the RU. For example, it can specify beamforming weights and so on. So it can be used to specify the, for example, the digital beamforming weights that you would add in your massive MIMO scenario.
Okay, thank you so much for the nice talk. I'll take this opportunity to give you a very big appreciation for the excellent and wonderful talk. Thank you for making time very early in the morning. I know the timing is not as easy because of the different time zones, but you made time and be with us. We thank you so much for this opportunity.